Hi, welcome. This is a broadcast for Chapter 10, and we are focusing on content relating to severe weather and things like tornadoes, ordinary air mass thunderstorms, and multi-cell storms. So we're going to take off on content that's related to Chapter 9, which was mid-latitude cyclone, cyclone, extratropical cyclone, or ordinary wave cyclone. So in class, we will have talked mostly about mid-latitude cyclones, and in some textbooks, they refer to those as different names. Most probably refer to a wave cyclone, or most commonly an extratropical cyclone. But in our region, we talk mostly about a mid-latitude cyclone. So cyclone in general is a circulation around a low pressure center. Hopefully you can recall some examples of these that we've discussed in class, like hurricanes, mid-latitude cyclones, and tornadoes. We will talk about tornadoes and the general pressures relating to storms, whether they be ordinary air mass thunderstorms or multi-cell storms or supercell storms in this discussion. Our next discussion will focus on hurricanes, which will be in a separate broadcast. So let's take off with thunderstorms. We have general characteristics relating to all thunderstorms on the planet, and you've experienced these before. These are the types of thunderstorms that forecasters in a certain region, like the Ohio Valley, Mississippi Valley, or the Tennessee River Valley, is going to talk about things like popcorn showers, pop-up showers, isolated thunder showers, and these are all thunderstorms that generate these types of things you see on the screen, whether it be lightning, whether it be thunder, whether it be those types of things that you have that are very obvious to us. So when we have lightning, thunder, and winds, those are going to be things that definitely compare to that. So those are all things that we can certainly see in that connection. There are two types of thunderstorms that we'll talk about, and that's what I'd like to focus on here. So the two types of thunderstorms that we'll look at here are going to be upcoming. The air mass thunderstorms are one that's mostly impacting an area around our region that would be isolated to the springtime. So think springtime events. These are going to be thunderstorms where we might delay a game. We'll go to the dugout, or we'll go to a vehicle if it's a football game, and then we'll let that thunderstorm pass, and we'll come back out and we'll finish the event. It's not an overly aggressive event. This is an event where we're having some type of a track meet outside, and we might have a brief delay in that, and then it moves on. This is the event where we have maybe Floyd Central and it receives rain. However, we might have another school in a small county like Floyd County not receive rain. Those are ordinary air mass thunderstorms. Do connect those to unstable environments. Air lifts easily, and that's why they're connected to the spring. So spring season, we have this warming trend, and that creates an unstable air environment. We do connect those to a cumulonimbus cloud, and those are the vertically developing clouds that we've talked about in class. And those are three things that we should make connections to. What we did not have a lecture presentation over was different air masses. This is maritime tropical. So with our first type of thunderstorm that I'd like you to remember, we have four connecting points here. We have air mass thunderstorms that are unstable, cumulonimbus clouds focused with maritime tropical air mass. That means it's warm and it's humid air mass. Severe thunderstorms is a different category. So severe thunderstorms are more aggressive. These are thunderstorms that do cancel events, that we do schedule things around. Why? Because we have high winds, hail, property damage, and we have most concerning flash floods. Flash floods is what claims most lives annually in regards to severe weather. It's not our tornadoes, it's not drought, but over time, when we average it out, most people are affected in this nation by flash floods, mainly because of vehicular decisions, trying to drive through water that's too high, moving too fast, or they're in unfamiliar territory. We can also connect tornadoes to this. So we do have a violence factor that increases quite a bit. So here are four things that I would like for you to remember with severe thunderstorms: high winds, hail, flash floods, and tornadoes are severe thunderstorms. We do not delay games because of this. We cancel games because of this. This would cause a warning situation with a severe thunderstorm, potentially. This is where we might go to the basement portion of the building at Floyd Central during certain events. Air mass thunderstorms, no. You can see an air mass thunderstorm outside of a window, but most of the time you're not going to seek shelter to an interior space. They're not that aggressive. So two types of thunderstorms there, air mass thunderstorms and severe thunderstorms. Severe thunderstorms are the result of uneven heating. Remember our conduction, convection, and radiation. They can be because of that, and that's why they're springtime. They can be associated with frontal lifting, predominantly cold fronts moving through a warm, humid environment. And as the recording of this time frame, we've had another outbreak in early severe weather in Oklahoma, with fatalities associated with those because of strong, unusually strong tornadoes for this time of the year, as we are only at the end of March. So that's an unfortunate situation, definitely relating to a cold front moving through unusually warm, humid air with high relative humidities. So we had a beautiful block of weather that was about 36 hours long, and we had temperatures that were in the upper 70s, lower 80s, and we had a very strong cold front move through there, generating a lot of spin-ups and a lot of cyclones, and some of those supercells that were generated, although they weren't massive, they did have the ability to produce some unusually strong tornadoes because of that. Diverging winds are things that can also be effective, be an effective generator of these. So three things that can cause these severe thunderstorms: uneven heating, frontal lifting, think like cold fronts, and diverging winds. Diverging winds are winds that are spreading out and moving away from one another. And we'll have a little bit more on that topic when we get to that part of the cyclone discussion about tornadoes. Here's our ordinary air mass thunderstorm ingredients. We have three stages here that you need to look at. We have our cumulus stage. The cumulus stage is just where air is moving up. We have our mature stage. Our mature stage is where we have not only air moving up in this environment, but we also have cold air moving down in that environment. So what we have there is two different types of situations. This is where we get our heavy rain from in this area, which is why we also may have certain types of hail associated with those. Be familiar with your density discussions here. We have cooler, more dense air that's able to sink more aggressively because of its greater density, and gravity is able to affect that with more force. And then we have the unstable nature of warm air moving up. So this is a system that is fueled by warm air. The more warm air is down here, the more buoyant it is, and the more aggressive it's going to be to rise. So if this storm is moving, say, to the east, and as it moves to the east, it's supposed to be an arrow pointing to the right. As that moves to the east, say that it's moving into increasingly warm air. These storms will not die down. They will become more aggressive. And that's what we see with a lot of these storms that will be captioned out throughout this presentation. And then we have the dissipation stage. So overall, this air thunderstorm system is going to be about 45 minutes, and then it's gone. That's why we can delay a game. We can delay a race. We can pull the tarps out over a professional baseball game field, and then continue that game after the ordinary air mass thunderstorm passes by. Stages of development here: cumulus, mature, dissipating. Those are the stages you need to work on putting into your memory banks. Nothing too aggressive as far as detail with those, but cumulus, mature, dissipating are the three stages of normal air mass thunderstorms. So take some time to look through these. You can either pause the presentation or use your textbook or the PowerPoints that are embedded in a separate file. Do be aware of entrainment. Entrainment is a powerful process without the influx of cool, dry air. If we have too much of that, if we don't have enough of that, we need a certain balance, and those are the things that cause these thunderstorms to be sustained. If we have too much entrainment, then the thunderstorm gets strangled out. If we don't have enough entrainment, then we have just a buoyancy factor there that can continue and move into a different category. So entrainment is this cool, dry air being brought in, and it helps fuel the processes of these downdrafts. Stages of development: mature stage, that's going to be the most intense phase, lightning, small hail. By small hail, think the size of BBs, peas, small ball bearings, those types of things is what we'd be associated with. Not much property damage. Cool downdrafts, you've probably been underneath one of these storms and felt those before. And then the death of it all is the dissipating stage. And that's where the entrainment and those types of evaporative processes are really at their height there. Air mass thunderstorms, as they move through, you can see how this is uplifting, and this air is being uplifted here, and this would be because of this boundary between the cool, dry air, that's cooler, drier air that's moving down. So as it moves up, we've got this cooler, drier air wedging underneath that, and that produces something down here at the bottom. That's our gust front. That's why it's usually windy in this area. And you've undoubtedly noticed that the winds pick up just right before, seems like minutes before, we have a heavy downburst of cold rain. And we could even have some hail associated with that too. So there's a small sliver that might be a little bit of hail associated with those in a certain geography as that storm moves over certain locations on the planet. All this is associated typically with either unequal heating, or this is implicating a lift force that is a cold front as well, potentially. So diagrammatically there, we can discuss those and defend that rationale within these illustrations. Occurrence, well, mountain regions like the Rockies, Appalachians, we have the greater number of air mass thunderstorms, mainly because of orographic process. You get a lot of differences in temperatures there, no big surprises there. Moving on to severe thunderstorms, we're having similar things except much more aggressive. We have heavier downpours, therefore we have greater flash flooding events. That flash flooding is very dangerous. We can see some local effects here in the year that this is being recorded on, and we can certainly recall some of those historic events as well. Probably the most catastrophic event from flash flooding in our nation is the Big Thompson Canyon event. And we will talk about that in class. And that is a very tough geography to be in when we look at those types of situations. And it's a very challenging situation with our flash flooding. Straight line wind gusts, we can have those. Those are things that we refer to as like bow echoes. Sometimes we can have that, and those can be affected by shearing winds aloft also. And sometimes those are called derechos, and we can see how those are affecting certain building structures whenever we have our discussions in class. They can be damaging, not necessarily so much as tornadic, but in just a gust front, typically implicating unimproved structures. So structures like a large walled barn, structures like a silo, structure like a very tall industrial building that has walls that might be 15, 20, 30 or more feet tall, but they're not made of concrete. They are typically made of a veneer that is like wood, metal. By sheet metal, that would be your typical stamped sheet metal, or it would be potentially, we see some cases where we have a brick facade. So we don't have that reinforced structure. If we have a poured concrete structure, it's a tilt-up building, we don't have that effect. Moving on, we have hail and lightning associated with those. Wind shear, and that's definitely going to be things. By wind shearing, we have two winds that are behaving like this. One is moving like that. The other is moving like that. That creates a great deal of force in the middle of these, and that can be very problematic. That's one of the things that makes tornadoes so destructive. And they can overshoot. They can enter the stratosphere. Overshooting clouds are doing this. Whenever we have the cloud base, and then we have clouds that come up like this, every so often those clouds will meet the top of the troposphere right there. And then they go into the tropopause, and then they can go into the stratosphere if they overshoot. And what causes them to overshoot is uncharacteristically warm air moving up. If that warm air here is extremely warm, very humid, then they can actually break through the tropopause into the stratosphere. So if that's the tropopause right here, then the stratosphere would be the next layer. And then what we're seeing is some of these clouds can actually temporarily exist right in there. So you know the name of those clouds. Those are the ones that are the most majestic looking and almost picturesque. They capture our artist's attention quite often in the natural scenes, and that's the cumulonimbus. Downdraft, and that's preceding the gust front. In our last slide, we saw those. Supercell thunderstorms, when these multi-cells get together, and by multi-cells, check this out. Here's one, here's two, and I'm looking at slide B. The highlighter's getting a little bit washed out there. So we got three multi-cells right in this image right there. So when those get together, then we have what's known as a supercell. Supercells are real deals. They're very dangerous. They do have the ability to have multiple tornadoes, and often those tornadoes have multiple vortices within each tornado. But here, the slide is trying to convey quite a bit of information, and this gets a bit jumbled up, so we will spend more time on this in class. We have first, what most of you understand is a gust front that's associated with a cold front. So if you look at the boundary that's bowing out at the lower part of this diagram, right there, we have a gust front, and that is a cold front. So that must mean, common sense, that right here, right in this area, this must be warm air. And that's why a lot of people notice that when we have severe weather, we typically have a drastic change in temperature. So the culprit is always cold air. Well, what caused it? The cold air. The cold air. And the reason why we think that is because all the air back here is cold. So behind it, we have cold. In front of it, we have warm. But we have so much more at roll besides that. What we have is a conveyor mechanism. We have a mesocyclonic features taking place. We have mid-level winds. We have upper-level winds. And they're all working to create this situation that's highly unstable, borderline erratic. And we're doing the best that we can meteorologically to try to track where these tornadoes will form and where they go, which is a hard science. So to do that, what we need to track is what's going on in some of the most violent thunderstorms on the planet. And that is a difficult task in itself, particularly looking at all of this interaction that's taking place in each one of these. And then they jumble together and create that. So it's a very, very tough task. So what we do is try to shorten our time that allows the dissemination of information. We try to broadcast and send that information out as quickly as possible, but as accurately as possible, which gives us very, very, very little lead time, and it makes people frustrated. So what are we looking at here? We're looking at where the gust front is, where is the most unstable air, what is the storm direction that's taking place, where's this overrunning taking place, and then is there mesocyclonic activity and uplift within a shearing environment that's going to be conducive to tornadoes. And those are the situations that cause these types of storms. Very luminous. That's the bottom of a supercell, is the shelf mechanism of it. And you can see how well organized that is. So it's pretty amazing how well organized something as chaotic as this can look in our natural world. So let's look at a few characteristics of supercells. Extremely dangerous weather. Single powerful cell, we're talking about 20 kilometers or more. The clouds can be 20 to 50 kilometers in diameter, which is an amazing, you're talking about differences there that would be much wider than the county that you're in. So easily covering a region within a state. So they are certainly conducive to a lot of damage. Mesocyclones, these are vertical winds that are going to cause an updraft to rotate. And we saw some of those in our last slide. Tornadoes will often form with mesocyclones. Squall lines, these are often referred to as gust fronts. These are bowing mechanisms. So what happens with squall lines is whenever a gust front moves through, or whenever a cold front moves through, the squall line is going to be an intense line of thunderstorms. And that squall line is going to form a line just like it is in yellow there. And along that line, we're going to have some pretty aggressive activity. What we have here is continental tropical air that's pulled into the warm sector of a mid-latitude cyclone. Remember, the warm sector of a mid-latitude cyclone, if you can remember our last discussions, we have a warm front here, and then here we have the cold front. These are little triangles. And our warm sector would be right here. So when we have continental tropical air pulled into the warm sector of a mid-latitude cyclone, we can get squall lines formed. That acts as the fuel, and they continue to form along a dry line. And dry line is going to be something that's important there. We see dry line activity in Oklahoma, North Texas. We see some of those in portions of the world that we typically refer to as our classic tornado alley. And that would be something that we challenge in this discussion. There is an abrupt change in moisture. Okay, not necessarily temperature, that kind of follows, but it's an abrupt change in moisture, and that's one of the things that we look at carefully. That's why in this course earlier we focused on humidity, and we have focused on relative humidity. Here is your momentous clouds. So those were mentioned in our last slide, and they are also mentioned very well in your textbook. Often these types of clouds that look luminous, they are typically in an area where you're getting a lot of wind activity and the wind is cool. And the reason why is because you are in the warm sector and what is bearing down upon you is a front. And that front is causing a lot of downdrafting, cooler air that goes into that. So very aggressive when you look at it. Not an overly aggressive tornadic situation necessarily. It can have some association to that, but not always. When we look at this mesoscale convective complex, this is similar to a supercell, and this is an aggressive situation as well. Probably not as aggressive statistically as supercells, but what we're going to do is take many individual thunderstorms, and we're going to put those together. They can be very large. They can be fairly well organized and cover a large part of geography in the nation. However, overall, that may not be quite as aggressive as the intensity, and by aggressiveness, I mean the violence as an intensity of a supercell. It is an oval shape and circular cluster, but check out the size. We're talking about 100,000 square kilometers. So these are massive compared to supercells. So that's a big reason why the intensity, the violence of these mesoscales are not quite comparable to the supercell. A supercell is much more packed. A supercell is much more violent in a very specific geography, which is big. It can be a whole county or two in size. And, you know, when we get out there, that 50 kilometers, that's certainly noteworthy. However, when we go to a mesoscale convective complex or an MCC, that MCC is massive compared to that. They are slow moving. We definitely want to track a flash flood type of an event with those. We can have flooding on several areas. That could be from small estuaries to major rivers, and it can then even extend to areas that typically don't carry water very well. So we're seeing those types of events associated with these. 12 hours, that's part of the problem. They don't last short periods of time. They last very long periods of time, so half of a day, and that's an aggressive time frame for rain at this intensity. They are going to form in the Great Plains. Every so often, they'll get as far east as the Ohio River Valley. I can remember a handful of these, and when they do, it's pretty aggressive rainfall, but they often don't have the effect. The MCC often doesn't have the effect that it does to our west. Lightning and thunder. When we see these types of things, lightning casualties in the U.S. are statistically broken down by this slide. We see most people being affected in open areas. These are sports fields, and it's definitely us. As far as I'm aware, from my history, I am not aware of any student at Floyd Central being struck by lightning. We have had some students in areas not in this county being struck. So there are teams that we play in the Hoosier Hill Conference that have had players on sports fields during the afternoon that have been indirectly struck by lightning. And that's definitely been in the recent past. And we'll talk about some of those. Many of those people are seeking shelter. The majority are out in the sports field. They just don't expect lightning to strike. Why? Because the storm doesn't have any thunder associated with it. It's not even raining. We just have those cellular features that are cloud-like. They're a little bit dark, but that we don't have anything violent that's out there. And so there doesn't seem to be anything concerning. And then out of the blue, out of nowhere comes a bolt of lightning, and they're the first victim. Keeping in mind that we're putting students outside on football fields, on track, on soccer fields during the afternoon, and that coincides with the most likely time that thunderstorms happen. So a lot of times when we find out about the severe nature of a thunderstorm is the same time that we're exiting a building at a high school level, putting players on fields, getting ready for their extracurricular activity. Those that do see the rainfall occurring, they might seek shelter under trees, which is a bad idea. Many of those are water-related activities as well. They might be in a swimming pool, might be in the water, might be on a boat, and we have those at 14%. Golfing is not a real big deal. We see 6%. That is something that's in the top 4, but it is not in the top 3. So for our purpose here, top 3 are big ones. Put those in memory banks. Open areas, so open areas being your football field, your soccer field, so on and so forth. And then under a tree, no, don't want to do that. But we do see people doing that. It's almost an intuition. That's a part of our DNA, apparently, that we want to seek that shelter. We want to go under a tree. And that's where a lot of those lightning victims are seeking shelter at. And then the third is water-related activity. We do have 6% in golfing. We have 5% agriculture-related. Corded telephone, we're phasing that out for some pretty obvious reasons. We're just not using the corded telephone as much in society anymore. And then golfing, this is kind of a unique, a golfing while mistakenly seeking shelter under trees. So this would be people that fall into the golfing category, but they took another step. Instead of continuing on with their game, they stopped, and what they did was they sought shelter, but where they sought shelter was under a tree. So it's kind of like they're related to two. And but in their mind, they were doing something that was relatively safe. Most likely what would happen is it started raining fairly aggressively, and they finished up one hole and they were in between, so they got under a tree. They were going to let the rain pass, and then unfortunately a lightning bolt occurred and it struck the tree or nearby where they were standing, and they fell victim. Then radio and handheld equipment, got to watch that a little bit. We do still do those types of things, but there's not a great statistic within that. So what causes this lightning? Well, we've got charges in clouds. Think of battery. We've got positive at the top, we've got negative at the bottom, and then we definitely have positive. I know you can't see it very well on this slide, but you have positive charges down here at the bottom. So you know that positives and negatives attract, and because of that polarity difference, what we see is negative charges filtering down. And then when they do create that, then what we have an ionized channel that takes place. That's your step leaders. So those are potential pathways. Then all of a sudden is we have a positive flow upward, and then we have a bright return stroke, and that carries the charges which has been deposited on the path downward. And so that bright return stroke is what we see. Typically, we don't see the others. Those are typically occurrences that happens too fast. And that return stroke can be multiple. That's what this slide is trying to show in the lower left, that there can be multiple discharges of negativity throughout that channel once it's established. And so it can be several return strokes, and a lot of times we just see one. But you've seen lightning flicker in the same channel more than once, and that's because there's multiple bolts carrying charge through the same pathway. Flash is a total discharge, 1/10 of a second. It's hard for us to see that. It really challenges our nervous system to be able to digest what it is that we see. This is such a high level of energy, especially when we get to step leaders. It's what we can see, and it contains multiple strokes. The leader is ionized air, it forms a path. We don't see that unless we have some type of a ancillary discharge that takes place. The step leader extends earthward in a short, nearly invisible burst, and this is pretty amazing. So this, remember, this is kind of the trailblazer, if you will. The leader is looking for is the scout. So this is the scout. Once the scout finds a trail, then it sends for the step leader. The step leader then blazes the trail. Then we can have the flash, and then bam, then we have the actual return stroke, and that extends upward from the ground to the cloud. And then we have the overall flash, and that's what we see, and it contains multiple strokes. So those are the ones that we need to make sure we can connect to. So the return stroke is upward from the cloud, upward from the ground to the cloud, and then the flash, 1/10 of a second, and it contains multiple strokes, and that's where we see those being discharged. Thunder is quick heating, is what this is. 33,000 degrees Celsius. It expands explosively, promotes sound waves, this rumble of thunder, and it really produces a great deal of low frequency waves. So 330 meters per second is what we're seeing there, and that can definitely rumble your geography. You can feel the ground shake, you can hear glass shake in windows, you can feel desks that you're sitting at shake. It's a very noticeable sensation. If lightning is more than 20 kilometers away, thunder is not heard. So those are things that we can understand. So can we use lightning and thunder to detect the motion of a storm? Absolutely. We can do this simple counting, and we've got a 5-second rule in there that we'll talk about in class. And it's certainly one of those things that's good for outdoor safety. Let's move on into tornadoes, twisters, cyclones, violent windstorms is what they have. Connect this to something known as a vortex. That's an upspin cyclone or a cyclonic rotation that's very intense. Pressures can be about 10% lower than the immediate outside of the storm. So inside thunderstorms, we have low pressure, but inside the thunderstorms, when we have tornadoes, we have about a 10% lower value than outside the storm. So we can have multiple vortices, and each one of those vortices could have an average of about 10% lower in the environment. Here's what we see with these by multiple vortices. Here we have 1, 2, 3, all within a tornado. So these are multiple tornadoes within a tornado. So the outside silhouette of this is a tornado. So that is the tornado that we're going to see on radar. What we don't see on radar, or implicated by or suggested by radar, what we don't see very well, or what we don't even detect very well, even after it's gone through, is multiple vortices. So in reality, a tornado that is fairly large is going to have 3 different types of vortices. We have 1, 2, and 3. So that means a building can get hit by 3 different tornadoes, even though it looks like it's just being hit by one. And we can use the post-storm study of Henryville, and whenever that building was struck, we can certainly reinforce this understanding. So pretty amazing. Overall development of tornado, 3 steps I'd like you to remember here. First, let's make sure we understand this horizontal axis that's spinning right there. And that horizontal axis has got a vortice that's pretty impressive, but it's not really implicating anything on the ground because it's aloft, still in the troposphere, but it's aloft. And it's not vertical, it is horizontal. So it's spinning, it's rolling fast, but it's not really affecting anything. This is a big reason why a lot of times you see clouds that seem to roll. Those are a bit concerning. Now, if we have a nice warm day, like in the spring, and the ground, remember our uneven heating? If our ground down here gets really warm, we have that updraft, then we have an alarming situation. If that updraft is strong enough and it really lifts the air aggressively, like right here, and that's in the afternoon, say 3, 4, 5, and it's had all day to get really warm, then that vortice, which is spinning, could be hundreds of miles an hour that is spinning, and as that spins, it's going to lift that up. And if it lifts it up, then all of a sudden we have an inflow pattern that's aggressive. That inflow pattern, which is mesocyclonic, counterclockwise, is going to enhance the updraft. And that updraft then, that inflow region, that air inflow, is then going to start to really spin upward. And that's where we get our tornado development there. So we have to have 3 things there that I'd like you to remember for the course. 1, we need a vortice that starts out. We need winds that are really fast moving above us. We're not going to feel that. We might see it in some type of weird storm like this and not be able to see the interior of it, but we've got these winds that are spinning like this that we can't necessarily see super well. Then we have to have the warm ground. The warm ground is what's indicated by this updraft. That warm ground is going to lift that vortice up, and as it lifts that mesocyclonic vortice up, then if it goes vertical opposed to horizontal, then we can have a tornado. And that's where we have the 3 ingredients that take place there. So the vortice, updraft, and then we have to have this vertical motion. It has to go vertical, and once we have that, then we have notice how it gets kind of cut off. Then we have an entity that can really start to create a lot of violence. Climatology, squall lines, cold fronts, these are all things that go into tornadoes. So what is it that causes them? We need squall lines, especially if we have bow echoing or gust fronts there. That can be pretty significant. So we do need a squall line. We need that pushing of that cold front moving out there. We're going to see continental polar and maritime tropical air meet, and that's where a lot of people say that it's the cold front's fault. We see it in the Midwestern United States, and we see about 150 to 600 meters in diameter. Travels about 45 kilometers per hour. Doesn't seem very fast, but remember, they don't have to take a break when they go through a school or a forest or a city. They just keep going. They don't have to follow roadways, but your vehicle does. So it's hard to outrun these, and it's definitely not encouraged. The path is about 26 kilometers long. Most travel to the northeast, and they exist between somewhere around 3 hours to less than 3 minutes. So we do have quite a bit of a discrepancy when we see those. The stronger ones can last, unfortunately, for a great deal of time. The shorter ones can last for just a few seconds, the less intense. Wind speeds can be less than 150 kilometers and over 500 kilometers per hour. So when we look at those, it's pretty aggressive as far as the overall. There's probably an F6 tornado, the traditional scale being an EFO to an EF5. Most likely there's an EF6 out there. We just don't have the instrumentation that's able to withstand those wind fields, especially when we achieve greater amounts than that. And when we get into those wind fields, we just don't have much that we build that can survive that to provide the data. When we see the development of occurrences, we do see these as a common thread. Look at the dates. Spring, early summer. That's where we enter our season. So our tornado season in North America, which is the greatest place for tornadoes on the planet, is definitely spring. So when we see these types of extremes and we see the most deadly and the single greatest amount of damage, notice how we are on that list as far as a state. We've got Indiana there. We've got Oklahoma. We're close to a lot of these. But when we look at these types of states, when we are on the verge of these types of locations as well. So it is something we need to be aware of, not overly concerned about, but aware of. So how many times does Indiana get hit by tornadoes compared to other parts of the nation? Well, we fall into a category if we consider the amount of tornadoes, the average number of tornadoes per year over a 35-year total going until 1993, then we see about 20. We see 20 within that average per year, and that would be over a 35-year total. We have 666. So Indiana had 666 tornadoes, and with that averaged out about 20 per year over that time frame. No surprise here that Texas has the most. It goes to the one with the most geography, and that's a big state, so it's going to have the greatest amount, the greatest aggregate there. Oklahoma, you see how that's pretty impressive. So definitely a big pocket in that area. But let's take a look at a different perspective here. Let's look at the amount of tornadoes in 10,000 square miles. Let's don't do it per year. Let's break it down a little bit more equivocal. So let's say 10,000 square miles. How does Indiana stack up? Then it becomes a little more apparent that Indiana might actually be a part of a second tornado alley or a tornado avenue at least. So while Oklahoma, Texas, and when we get into areas in our traditional dry line configurations of the southern Midwest, then we can definitely see pockets where they're getting about 9 per 10,000 square miles or 7 per 10,000 square miles per year. But we are certainly in the upper category of occurrence there as well. And then look at Florida. It's also pretty aggressive as well. Tornado destruction, you've seen some of these before. We won't dwell on this. A lot of times the tornado destruction is at the expense of somebody's life, or definitely at the expense of somebody's property or way of life. So we are aware of the destruction that tornadoes can do. And for this course purpose, it's very apparent that their power is often underappreciated, and we so often don't take the precautionary steps when we do have a tornado warning and or tornado watch. So that's something I'd like you to really work on, is trying to become a little bit more sensitive to those, at least having a plan or a near exit strategy for those types of events if they affect your location. Tornado intensity is up next. We have this scale. The E stands for enhanced. An enhanced Fujita scale has replaced the original Fujita scale. Unfortunately, the Fujita scale is still out there, still published, and still broadcast around the nation. But we are going to recognize the enhanced Fujita scale. What's the difference? The amount of damage, how we discuss the damage profile. It gives us a greater articulation of wind speeds, so it's not as broad, so it helps us discuss that event a little bit better. No surprise here, the loss of life. This chart shows that when we have fatalities like this that go up, what happens is the most strong tornadoes, which is here, is what's at culprit there. So the stronger tornadoes cause a greater amount of life loss. However, the benefit of that is that the stronger tornadoes only occur in small values. We don't have that many real strong tornadoes. We have several weak tornadoes, but we typically do not have nearly the loss of life because we're getting better at being prepared. And hopefully, this reflects an improved building code situation across the nation. So maybe our structures are getting a little bit better. Tornado watches and warnings, hopefully, you know this already. We'll reinforce it. Watches are something that we need to be alert of a situation. And when we have a warning, that is something that we need to make certain that we are taking cover with. That means we do have a tornado that's been spotted. So we have a warning that has a tornado actually sighted. And when we have a watch, we have conditions that are favorable. They usually cover an area of about 26,000 kilometers, and they can last about 3 hours or longer. So unfortunately, we don't pay that much attention to watches. We need to, especially if you've got a doubleheader baseball game, or if you've got if you're running a marathon or doing something that's going to be outside for long periods of time, and you have a watch. A watch can easily turn into a warning within minutes, because that can be a situation that's very dangerous. So do be aware of your situations and how those are used as far as communication devices. There is high probability of imminent danger, and they're usually for a much smaller area over a shorter period of time, 30 to 60 minutes. Doppler radar is a tool that's used that we've looked at in class before. This is one of the tools that are used to try to determine where tornadoes are, if they're present, where they're going. Normally, we need to have overlapping radar. 2 or more, ideally more is better. It gives us a little more information there. And we have a hooked shape echo region, and that's because the inflow and outflow boundaries, as precipitation, moisture, moves into and away from, moves toward or away from a antenna receiver, a Doppler radar. So the way that it works is similar to this, and we'll talk about this more in class, similar to things in astronomy as well. Whenever you have a wave that's moving toward an observer here, we're going to have wave compressions, and those waves are going to have a higher pitch, where the other way is just the opposite. When we have a wavelength that is increasing from crest to crest, we're going to have a decreased value and a decreased amplitude, and not amplitude, we're going to have a decreased pitch. Therefore, it's going to sound like it's moving and getting lower, lower, lower as it moves away from you. There's several examples of sound. So that'll do it with chapter 10. Went through that at a pretty good pace, and I think overall you should have a decent understanding of a new view that you will have information about that we'll talk about in class, and that should help hopefully clarify some of those contents. Thanks for tuning in. See you in class.